Okay, so this next section is about spectrometry. Specifically, in this book, they're talking about spectrophotometry. And basically, that's using light to analyze chemical reactions or solutions or things like that. This is a spectrometer right here. And what this is this little symbol here means light. Light enters the source, and then it goes to the recorder, and the amount of light absorbed is recorded. And so let me show you what that kind of looks like. I'm going to plug this in to my computer. I wish there was a way for me just to share my computer screen with you, but Zoom doesn't allow me to do that. So I have to stop and create a new share. But what I'm going to do here is I'm going to open up this let's see. I'm going to open up this spectral analysis software that I have. Now you can't see what's happening right now, but I'm going to show that to you in just a moment. So this is the software that I have. You can see that it says Vernier Spectral Analysis at the top. I can choose a bunch of different types of analyses. We're going to look at an absorbance analysis versus wavelength, full spectrum. And so I'm going to choose this. And this takes a while for the lamp to warm up. We're not going to warm it up because we're not doing a real analysis, but I'm going to skip this step. And we're supposed to put in a blank cuvette. So a blank cuvette is a sample that has solution in it, but none of the colored solution. So it's just clear and colorless. So I'm going to put calibrate. And when we look at the spectrum here, you'll notice that on the y-axis we have absorbance, and on the x-axis we have wavelength. And this spectrophotometer basically works with visible light that goes from 400 nanometers to about 650. It doesn't read much above 650, although we have lines here. And the color bar below shows you roughly the wavelength of light that corresponds to a particular color. So way on the left, we have violet, and then indigo, and then blue, and then green, yellow, orange, red, or VibGyor. If we do it backwards and go from 700 and do red, orange, yellow, it's Roy G. Biv. And you may have heard that before in the past, Roy G. Biv or VibGyor. So this is the VibGyor orientation. Now I'm going to switch my screen, my share with you, and I'm going to do a new share. And you can see that this is the sample I put in, and it is clear and colorless, as you can see on the white paper. Now what I'm going to do is we're going to get the absorbance spectrum of this yellow solution. So I'm going to put this in here, and then I'm going to change my share screen. And I'm going to go ahead and push collect data. So we're going to collect, and remember, I have that yellow sample in here. So we want to think about what we're going to see here. So absorbance means that wavelength of light is being absorbed. If you get a big number there, it's being absorbed. If you get a small number, it's not being absorbed. So why does the solution look yellow? Is it because yellow light is being absorbed, or yellow light is not being absorbed? And then they're the same for the other. You know, why is it that we don't see blue or something like that? So let's collect the data and see what happens. And here you can see it doesn't take very long. I'm going to stop this. And if we analyze this spectrum, do you see that the light that's from 400 nanometers to 550 basically is being absorbed. The violet, the indigo, the blue, the greens, they're being absorbed. Here, where the absorbance is very close to zero, these wavelengths are getting through. And so that's why the solution looks yellow. And you could even argue that the solution looked a little orangish. So that's why this solution looks the way it does. So now what I'm going to do is I'm going to take this solution out and I'm going to put in a solution that looks blue. So let's take a look and see what the solution that is blue looks like. And this will not overwrite this data, it will add to the data. So I want you to think about what the spectrum is going to look like for a blue solution. Where is it going to be low and where is it going to be high? Kind of a mental exercise here. And then I'm going to collect. So does everyone got kind of an idea what the blue solution will look like? Yay or nay? Just give me a thumbs up or thumbs down. Remember, the yellow solution, the absorbance was low in the yellow region. So for the blue solution, where do we expect the absorbance to be low? For the yellow solution, the absorbance is low in the yellow region. For a blue solution, and let me show you the blue solution. I'll do a quick switch screen here. So here's my blue solution, which I'm going to put into the instrument. So what do we think is going to happen here? Well, I'll tell you what I think. I think since it's a blue solution, this region here, where there's a lot of absorbance for the yellow solution, will be actually low for the blue one, and it should be higher over here in the yellow area. So let's take a look and collect. And sure enough, do you see how it's low in the blues, but it's higher in the yellows? Okay. All right, so that's spectrophotometry. Now let me go back to the notes. And let me put my spectrometer away. So here, in this particular example, we're going to study the nitrate ion, which is involved in the biochemical nitrogen cycle. We can determine the nitrite ion content of a sample by using spectrophotometry. By first using several organic compounds to form a colored compound from the iron, and then collecting the following data. So here, these are the concentrations of the different solutions with the nitrate ion in it. And this is the absorbance of that solution at 550 nanometers. Now, you like to work at a wavelength where there is a lot of absorbance so that if there's a change in concentration, you'll get a change in absorbance, because it turns out that absorbance is proportional to concentration. That is to say, if you increase the concentration, you increase the absorbance. So we need to construct a calibration plot, determine the slope and intercept, and then find the nitrate ion concentration for this unknown solution. So what I have here is a piece of graph paper. I'm going to flip this around. And what we're going to do here is we're going to plot this data, and I have a straight edge here. Now, if you take a look at this, we plot absorbance on the y-axis, and we plot concentration on the x-axis. And you can see my absorbance numbers go all the way up to 0.598, so about 0.6. And here, if you look at the concentrations, they go all the way to about 18. So what I'm going to do here is I'm just going to arbitrarily put a line down here like this. And I know that there's about 40 squares here. So I'm going to make this 18.00. And I think what I'm going to do is every 2 squares will be a 1, if you will. So this will be 17. This will be 16. this will be 15, and this will be 14.00. The reason I'm not writing numbers here because it'd be too crowded. Okay, so I'm going to continue. That would be 13, 12, 11, and 10. And so I'm going to check my spacing here. If I go over 4, I get 14. Go over 4 more, I get 18. And so this should be what? 6. And this is going to be 2. And then if that's 2, this will be 0 right here. So now I'm going to draw my vertical axis. And for the vertical axis, we've got to go all the way up to 0.6. So how many of these squares are there? Let's see, that's about 5, 10, 15, 20, 25. So there's about 28. 28 divided by 6 is 5. So I think what I'm going to do is every 4 of these is going to be 0.1. So I'm going to make this 0.1. Another 4 is going to be 0.2, 0.3, 0.4, 0.5, and 0.6. So this way I've used most of my graph. I haven't made it too small or too large. Now this is going to be concentration. And I'm going to put times 10 to the minus 6 molar. And so by doing this here, I don't have to put 10 to the minus 6 for every number here. Here, this is absorbance, and absorbance, it turns out, doesn't have any units because it's a ratio of values. So if I look at the data, you can see that I've got data at 2 and 0.065. So here's 2. That would be 0.5. This would be 0.75. So 0.65 would be somewhere around in here. And then I've got 6 and 0.205. 0.205 is right here. So 0.205 is just going to be a little above 0.2. Then I've got 10 and 0.338. So here's 0.3. Here's 0.35. So 0.338 should be a little less than 0.35. And then I've got 14 and 0.474. So 0.474 is about 3/4 of the way. So here, I'm going to make sure that when I'm so far away from the axes, I've got to make sure that I'm lining up on 14 and 4.75. So that looks good. And my last number is 18 and 0.598. So 0.598 puts it almost at 6, somewhere around here. And then let's see where 18 is. 18 is here. So you can see that I'm a little off here. I need to go 1 square over again. So there's my data plotted. And to get the calibration curve, you draw the best straight line you can for this data. So I'm going to draw something like this with my paper. I don't have a really long ruler. Okay, so there's my calibration curve. Now we need to get the equation of this line. So how do we do that? And the answer is we got to find 2 points on the line where it's easy to read the data for that point and then get the slope of the line. Can everyone see that this right here is right on a set of crosshairs? So I should be able to read that pretty easily. So this is 6, this is 7, so this has to be 6.5 precisely. And if this is 2 and this is 3, then this must be 2.25 precisely. And actually, I made a mistake. It's not 2.25, it's 0.225. So I want to find 2 points on the line that I can measure very precisely. And look at that. There's another one really close by where I can read the values very easily. So this value is 678. So this is 8.0 and 0.275. Okay. So let's use those values to get the slope of the line and the equation of the line. Now, why didn't I use this point here to get the slope? Because it's not on the line. Why am I not using that point? It's not on the line. Why am I not using that point? It's not on the line. You have to use points that are on the line to get the slope. And that's a mistake that a lot of people make. They just use 2 points they use to make the graph when you have to use 2 points that are on the line that you draw. Okay, so the slope. The slope is going to be the change in y over the change in x, and my 2 points are 8.0, 0.275, and 6.5, 0.225. So the y's are the last values, correct? So here I'm going to have 0.275 minus 0.225. And my x values are going to be 8.0 minus 6.5. So let's see what we get here. 0.275 minus 0.225, and then divided by parentheses 8 minus 6.5. So I get 0.033. I'm going to leave it at 2 zig figs. So that's my slope. Now, here's something we also have to remember, that these values are supposed to be times 10 to the minus 6. So this is really over times 10 to the minus 6, which really makes it 0.033 times 10 to the 6 for the slope. Okay, now the b-intercept. We have y is equal to mx plus b, which is really absorbance is m times concentration plus b. So absorbance minus m times c is equal to b. And I'm just going to plug in these numbers here to find out what my b is. Remember, the first is a, or the first is, I should say, x. So that's c. So I'm going to have 0.275 minus 0.033. And here I'm not going to use the 6 because it's going to kind of mess things up a little bit. Well, actually, I'm going to use it. Times 10 to the 6. And the slope, or the concentration, is 8. Now here, I've got to make sure I put 8 times 10 to the minus 6 is equal to b. Okay, so let's figure out what this is. 0.275 minus 0.033 second EE6 times 8 second EE negative 6. And so I get b is equal to 0.011. And so b is really close to 0, which is what we expected. So the equation for the line is that the absorbance is equal to 0.033 times 10 to the 6 times the concentration plus 0.011. In other words, the concentration is the absorbance minus 0.011 divided by 0.033 times 10 to the 6. So we're told that for our unknown solution here, the absorbance is 0.402. Now we can take a look here and see that 0.402 is around here and walk it over, and 0.402 is about right here. So we expect that the concentration will be between, let's see, this is 10, 11, 12. So this looks like it's about 11.7. 11.7 times 10 to the minus 6. Okay? So let's see what we get using the formula that we have for this. Okay, so 0.402 minus 0.011 over 0.033 times 10 to the 6. Plug all these numbers in. And I got to put this in scientific notation. And I get 1.2 times 10 to the minus 5. Now I'm going to multiply this by 10 to the minus 1 and times 10 to the plus 1. And when I do that, I'm multiplying by 1. I'm going to take these and combine them and get 10 to the minus 6, and take these and combine them and I get 12. So that's my concentration, 12 times 10 to the minus 6 molarity. And by using the graph, we got 11.7. So I would argue that this 11.7 and this 12 are essentially the same value. So that's how you do this spectrophotometry. So on your next homework assignment, you can expect to see a problem like this on it, where you're asked to do draw the calibration curve, get the equation of the line, and then figure out the concentration based on absorbance. Now, I guarantee you, that's something that you probably want to watch again. All right. The next section is about energy and some basic principles. So I just recorded a lecture on energy, the very first section here. And so I'll let you watch that. But basically here for this section, we're talking about energy and heat and how heat works in chemical reactions. So one of the first questions they ask you in the back of the book is, what determines the directionality of energy transfer as heat? So what they're talking about is, imagine you have a system and surroundings. And a common way to draw the system and surroundings is something like this. Here's the system, and here's the surroundings. So I want you to imagine, when they're talking about what determines the directionality of heat transfer, they're talking about something like this. Imagine the system is cold and the surrounding is hot. Which way will energy flow? If you think energy is going to flow into the system, put go faster. And if you think it's going to flow into the surroundings, put go slower. So into the system is go faster. Energy flowing into the surroundings is go slower. Go ahead and make a choice. It really doesn't matter what you choose right now because you haven't really been taught this. So make a choice that seems to make sense to you. Energy into the system is go faster. Energy into the surroundings is go slower. And so all of you picked energy going into the system, and you're exactly right. what happens is energy flows from hot to cold. So if I drew something like this, and made this cold and this hot, which way would energy flow? So if you think energy would flow into the surroundings, go slower. Into the system, go faster. Go ahead and make your choice on this one. The choices are the same. Into the surroundings, go slower. Into the system, go faster. Right. So what is the direction of heat flow? And the answer is from hot to cold. How long? So how long will this hot flow into this cold? How long will this hot flow into this cold? So here's the deal. This hand here is hot. This hand here is cold. So if heat is flowing from the hot into the cold, what happens to the temperature of the cold as it gains energy? It rises. But what happens to the hot as it loses energy or gives away energy? It lowers. So here the temperature of the cold gets hotter, the temperature of the hot gets colder, and then they reach the same temp, and then do they go past one another? Does this happen? So my question here is a yes or no question. Does this happen? And the answer is no, because what happens here is if energy flows from one into the other, one's going to get colder, one's going to get hotter. We don't see hot things getting hotter and cold things getting colder when we put them together, right? When you put ice and water together, you don't see the ice getting colder and then the water boiling. That doesn't happen. So when we say that the direction of heat flow is from hot to cold and we ask for how long, the how long is not a matter of time, it's a matter of what happens. So how long? Till both the system and the surroundings are the same temp. That's for how long. And we have a special name for that. It's called thermal equilibrium. Okay? So the shortwave answer to this would be how long until you reach thermal equilibrium? What does thermal equilibrium mean? It means when they reach the same temp. Okay. Now, we also assign sign to the direction of heat flow. So heat in is absorbed, and we call that positive and endothermic. And heat out is released or produced. I like the word produced. And we call that negative and exothermic. So you need to know these terms, exothermic, endothermic. Endothermic is positive, exothermic is negative. Furthermore, when we say heat in, heat is absorbed, the heat is a reactant. And here, heat is a product. So we want you to know those terms. And now let's take a look at a problem associated with that. So here we go. Energy, some basic principles. What determines the directionality of energy transfer of heat? Whichever is hot, energy will flow from it to the cold because hot flows from cold. Identify whether the following processes are exothermic, endothermic, and what is the sign, positive or negative. This Q is the symbol we use for heat. So Q is the symbol we use for heat energy. Okay, the reaction of sodium solid with chlorine gas. So that's a tough one if you've never seen the reaction before. So let's take a look at that on the internet. There is a picture in the book, but it's always more exciting to see this on the internet. So I'm going to go to my share, and I'm going to share the internet. There we go. And what I'm going to do is I'm going to put the reaction of sodium and chlorine. And we're going to look at a quick little video here. Well, actually, we'll just look at an image. Okay, so this is not a video, but inside of this container here, can everyone see the green gas inside of this container? If you can, give me a thumbs up. Okay, now through this little funnel, they're adding sodium. Now, when the sodium adds to this green gas, you can see that it looks like there's flame inside the container. And that's because the reaction is very, very hot. So it's releasing energy as light and as heat. And you can see that the reaction gets very, very hot. And then after a while, it starts to cool down. And you'll notice at the very bottom of this container, we still have some green gas, but we also have some white solid there. And you want to, oh, looks like we're going to add some more sodium here. Anyone want to venture a guess as to what this white solid is inside of this container? It's sodium chloride. Okay. Probably would have been more interesting if we watched a video. Let's see if we can see a quick video. Let's see. Video. "51 seconds, we got time for that.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
Okay, so that was kind of interesting. Now let me stop this, otherwise we're going to get another video.
One of the things you recognize being a professional athlete is that there's this whole ecosystem that happens around my training and my recovery.
Okay, now let me go to back to the share of the screen. Okay, so back to this. We're attempting to answer the question, the reaction of sodium plus chlorine. So what's happening here is sodium plus chlorine is making sodium chloride plus heat. So here, since heat is a product, it's produced. And so this is exothermic, and it's negative. Okay, The next one is cooling and condensing gaseous N2 to form liquid N2. So this is B. We're looking at taking gaseous N2 to form liquid N2. So is this going to absorb heat or release heat? Now, I'm going to move this over and tell you that this one confuses me. So what I do is I reverse it. I want to take N2 liquid and turn it into N2 gas. Now, I want to think about this in terms of water. If I want to take water and turn it into steam, do I have to add heat or does this release heat? So if you want to boil water, do you have to add heat or release heat? Well, you have to add it. So I'm going to put heat over here because the same thing would happen for nitrogen. To turn a liquid into a gas, you have to add heat. So heat is absorbed, which means this is endothermic and positive. And so that's how you go about doing that, right? So what about the reverse reaction? Well, it turns out the reverse reaction is exactly the reverse of this. So I'm going to reverse this reaction. I'm going to play a little joke on you first, okay? So I'm going to reverse this. Are you ready? Oops, did that wrong. Heat plus N2 liquid. You see what I'm doing there? So let's really reverse this. So I'm going to put N2 gas here, turning into N2 liquid plus heat. So that's reversing it. So it turns out that me looking at something that's easy for me to understand and reversing it and seeing that everything ends up on the other side helps me to understand this. So for this reaction here, heat is produced. So that means that this is exothermic. And since the reaction is losing heat, this is negative. So are there any questions on how I did B? Now, some of you are smart enough where you don't need to reverse this and make it make sense and then just accept the opposite. But this is what I do. Okay. Cooling a soft drink from 0 to negative 25 degrees Celsius. So this is C, cooling a soft drink. Now, naturally, your first inclination is to say, well, if I'm going to cool it, I'm going to add cold. But you can't add cold. Heat flows from hot to cold. You can't add cold and say that cold flows from cold to hot. There is no such thing as cold. There's just heat. So here, we're going to take a drink at 25 degrees Celsius and turn it into 0 degrees Celsius. So here's my drink. So this is another tough one for me, but I'm going to reverse it. What happens if I start with a drink at 0 degrees Celsius and turn it into a drink at 25 degrees Celsius? Do I add heat or does this produce heat? And to me, you have to add heat. So if this is the case that I have to add heat to warm up a cold drink, then that means to take a hot drink and cool it down, I have to remove heat. And so here we write down the heat as a product. You can't write a negative in a physical process. So this is heat being pulled away. This would be like you sticking something in the refrigerator and expecting it to cool down. And you might say, well, yeah, it expects to cool down, but there's no heat produced from that. And you're exactly wrong. If you go to the back of your refrigerator, you'll always find out it's hot there. Why is it always hot at the back of your refrigerator? And the answer is because it's pulling heat out of your objects and releasing it into the room. That's why refrigerators always make your room warmer. Okay, so here, heat is a product. It's produced. It's exothermic. And that has a negative value. There we go. Okay, so for the last one, D, you have to heat this mercury 2 oxide to form mercury and oxygen. Well, since you have to heat it, heat is a reactant. So if heat is a reactant, that means that it's absorbed, which means endothermic, and that's a positive value. So whenever your heat is a reactant, it's positive, endothermic. Whenever your heat is a product, it's negative, it's exothermic. All right? So these are some tough things to think about, but you got to figure them out. All right, moving on. The next section is a section called specific heat capacity. And specific heat capacity is a physical characteristic of any substance. Basically, specific heat capacity is the amount of energy that something can absorb and the accompanying temperature change. For instance, when you heat water to boil, the water seems to heat up very slowly. And that's because it takes a lot of energy to change the temperature of water. Whereas when you add the same energy to a frying pan, the frying pan heats up very quickly. That's because it doesn't take much energy to heat it up. Okay? So for specific heat capacity, this has the symbol C. And the definition of specific heat capacity, which you'll find in the lecture that you'll be able to view later today, it's the amount of energy required to heat 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So the specific heat capacity of water is 1 calorie per gram degree Celsius. It takes 1 calorie of energy to heat 1 gram of water by 1 degree Celsius. Now, it turns out that this is also equal to 1 calorie per gram per Kelvin. And the reason for this is that when you're doing this work here, the calorie is the heat, the grams is the mass, and this is the change in temp. So this little triangle means change in temp. Now, change in temp is the temp final minus the temp initial. So if you start off with something that happens to be 1 degree Celsius, and it ends up being 3 degrees Celsius, the change in temp is 2 degrees Celsius. Now, what is the Kelvin temp for 3 degrees Celsius? Well, the Kelvin temp happens to be 3 plus 273, 276. What's 1 degree Celsius in Kelvin? Well, it's 273 plus 1, 274 Kelvin. So here you get that the change in temp is 2K. Now, this does not say that 2K equals 2 degrees Celsius. This says that the change of 2 degrees Celsius equals the change of 2 Kelvin. So if we drew the two number lines here, degrees Celsius and Kelvin, here if you had 3 and 1, the same temps would be 276 and 274. So we're not saying 3 equals 276 and 1 equals 274. We're saying this difference is 2 and this difference is 2. The same difference, okay? So here, that's why these are equal, not because the degree Celsius equals a Kelvin, but because the change in temperature is the same. Now, sometimes we do this in joules, which means you would have 4.184 joules over gram degree Celsius, or 4.184 joules over gram Kelvin, because 4.184 is equal to 1 cal. This is exact because that's defined for water. Now, the specific heat capacity is different for different objects. I think for aluminum, it's a no, actually, let me think. For gold, it's like 0.113 calories. Gold has a much smaller specific heat capacity, which means it doesn't take much energy to change its temperature by 1 degree Celsius. So that means if you want to cook with a gold pan, it's going to be better than cooking with a water pan because the gold pan will heat up faster. It'll be a little more expensive. Okay, so that's the idea behind specific heat capacity. Let's take a look at this problem here. The specific heat capacity of benzene is 1.74 joules per gram K. What is its molar heat capacity in joules per mole K? So here, to do this, we need to take the 1.74 joules per gram K and turn that into joules per mole K. So basically, we have to turn grams into moles. Well, C6H6 has a molar mass of 6 times 12.01 grams plus 6 times 1.01 grams. So this is what? 72.06 grams plus 6.06 grams for 78.12 grams. So if we multiply by 78.12 grams per 1 mole, we will be able to calculate the molar specific heat capacity. And roughly we have 2 times 70, which is going to be around 140-ish. So 1.74 times 78.12, and we get 136 joules per mole K. So that's how we do that problem. Now you might be wondering, this one here I rounded up to 2, and this one I rounded down to 70. And I estimated the answer should be around 140, which turned out to be pretty close. This is what I do when I'm multiplying numbers together. If I round one up, I round another one down to even it out. Okay. Now, here's the next question. Let me move things up here a bit so we can focus on the question. How much energy is required to raise the temperature of 50 milliliters of water from 25.5 degrees Celsius to 28.75 degrees Celsius? And they have the density of water is 0.997 grams per milliliter. So that formula I gave you before can be used here, Q over M delta T. When they ask us for how much energy, that means Q. We want Q. So here I'm going to rearrange this to Q is equal to C M delta T. Now for those of you who want to be doctors, a lot of people have changed this yet again to Q equals MC delta T. because it looks like a lot like Q equals MCAT. And if you want to be a doctor, you know what the MCAT is. All right, but I like this way here. Now, for this particular problem, the specific heat capacity of water is 1 calorie per gram degree Celsius. The mass is going to be 50 milliliters, and we got to use the density. The mass is going to be 50 milliliters times 0.997 grams per liter, or per milliliter. So the density is going to be around 50, but a little less, right? So I get 400 or 49.85 grams. Now, what is the change in temp for this? The change in temp is the final temp minus the initial temp. So we're going to raise it from here to here. This is the final. This is the initial. I don't want to forget my units, so I'm just going to put it outside there like that. And you can see that this is roughly a 3-degree change plus a little bit more, right? 3.23. Yep. So I have the 3 values that I'm going to need for this calculation. And when I put them in, I'm going to get 1 times 10, 1 calorie per gram degree Celsius times the mass of 49.85 grams, and then times the change in temp, which is 3.23 degrees Celsius. So the grams cancel, degrees Celsius cancels. We're going to be left with calories. Here we have 4 significant figures. Here we have 3 significant figures. And in this value here, it's defined, so it has an infinite number of zig figs. So we're going to get 3 zig figs out of this answer. And basically, we're going to have something a little bit more than 150, like maybe 165, right? Because 3 times 50 is 150, so 3.23 must be more like 165, or maybe 160. So let's try it out. 49.85 times 3.23, and we get 161 calories. And there's your answer for that one. Give me a thumbs up if you're okay with that. Give me a thumbs down if you want to ask a question, or just turn your mic on and ask a question. Okay, well, I'm going to turn your thumbs off, and I'm going to ask you a question. Is this stuff that you'd seen before in your previous chemistry class? Give me a thumbs up if you've seen it. Give me a thumbs down if you haven't. Okay. The reason I ask is that this is stuff that is typically covered in a chemistry class in high school. And I'm trying to get a measure of what's happening in the high schools around town. Okay, next one. After absorbing 1.85 kilojoules of energy as heat, so we can say Q is 1.850 kilojoules. The temperature of a 0.500 kilogram block, so mass is 0.500 kilograms, of copper is 37 degrees Celsius. So here I'm going to put T final is 37 degrees Celsius. What is its initial temperature? So we know that Q equals Cm delta T. which means that Q is equal to CM T final minus T initial. And we want, this is what we want. So I'm going to rearrange this equation to Q divided by CM is equal to T final minus T initial. So what I did is I divided each side by CM. And now what I'm going to do is I'm going to subtract TF from each side. And then because I don't want a negative sign here, I'm going to change the sign on everything. So I'm going to have negative Q over CM plus T final is equal to T initial. And then just because I don't like this negative out in front, I'm going to rewrite this up here as T initial is equal to T final minus Q over CM. Now, the only thing that we don't have that we need is C, the specific heat capacity of copper. So what we do is we use our book and we look it up. And I don't remember what it is, but I'm sure we can find it. If you do have the 10th edition, this is on page 232, they tell us that the specific heat capacity of water is 0.385. For copper is 0.385 joules per gram K, or I should say degrees Celsius, because that's the same as per K. So we have our Q, we have our mass, we have our initial temperature, and now all we have to do is figure out the final, or the final temperature, I'm sorry. All we have to do is figure out the initial. So Ti is equal to 37 degrees Celsius minus 1850 kilojoules over 0.500 kilojoules. That's the mass, and the specific heat capacity is 0.385 joules per gram degree Celsius. Now you might be thinking, oh my goodness, he's going to get into trouble here because he's got kilojoules and joules here and so forth. And actually, I'm not going to be in too much trouble because this kilojoules, oh, this is kilograms. This K cancels with this K. This joule cancels with this joule. This gram cancels with this gram. And we're left with degrees Celsius on the bottom, which means we're going to end up with degrees Celsius on the top. So we got 37 degrees Celsius minus degrees Celsius, and we just have to plug these numbers in. So that's kind of one of the neat things about prefixes is a prefix can cancel with a prefix, regardless of whether they belong to the same type of unit. So 1850 kilojoules over 0.500 kilograms, the K's actually cancel. And that's okay. All right, so let me plug these numbers in here. 1850 divided by 0.5 and divided by 0.385. And I get 9610 degrees Celsius. Okay, at first I was thinking to myself, I must have screwed up, and I think I did somehow, but I got to figure out how. Let me think about this. Does anyone see where my mistake was? How does this look? This is gold. This is gold. This is gold. I think this is gold, and I think this is gold.
Wait, is it on the initial calculation? 37 degree minus, is that supposed to be 1.850 or?
Ah, on, good eyes.
Okay, yeah.
850, not 1,850. So it's 9.6, not 9,610. And 37 minus 9.610. So we get 27 degrees Celsius is our answer. And that makes more sense because when you read the problem, after absorbing 1.850 kilojoules of energy as heat, the temperature is 37. You expect the initial temperature to be lower than 37, but not negative, not a negative value. Okay, thank you, An. Good job. All right, so that's specific heat capacity. Here's a couple more specific heat capacity problems. The first one at the top is actually the hard one. So we're going to look at the second one here. And this question here is going to be something that you guys are going to be actually working with as one of your labs this week. So this is a way to figure out the specific heat capacity of molybdenum. So you weigh a piece of a molybdenum, it's 237 grams, and you heat it to 100 degrees Celsius. Now, how do you heat an object to 100 degrees Celsius? And the answer is really simple. Put it in boiling water for a while. Water boils at 100 degrees Celsius. And if your molybdenum is colder than the boiling water, what will happen to the molybdenum? Heat will enter it. And that molybdenum will get hotter and hotter. Now, what keeps your boiling water from getting colder? And the answer is you're putting heat into it from your stove. So this is in a pot. The pot's getting hot because you're adding heat. The water's boiling, and as long as the water boils, it's at 100 degrees Celsius. So when you put the molybdenum in there, eventually it will get to be 100 degrees Celsius. Will the molybdenum get hotter than 100 degrees Celsius? And the answer is it shouldn't. It could, though, if it's in contact with the pot right above the flame. Okay? So you want to put the molybdenum off to the edge of the pot, away from the flame, where it will reach equilibrium with the water temp. Okay, so you drop it into 244 grams of water at 10 degrees Celsius. So they're talking about the water starting at 10 degrees Celsius. So if I draw this out, here's the water at 10 degrees Celsius, and here's the molybdenum, Mo. And for the water, we have 244 grams, and this is 237 grams. And this is T initial for the water, and T initial for the molybdenum is 100 degrees Celsius. So does everyone understand the concept here? Now we're going to put the molybdenum in the water. So naturally, it's going to make the surface of the water rise. And here's the molybdenum. And here, T final, they tell us is 15.3 degrees Celsius. So is this the final temp of the water, the final temp of the molybdenum, or both? What do you think? If you think it's the molybdenum, say yes. If you think it's the water, say no. If you think it's both, pick go slower. So yes is molybdenum, no is water, both is go slower. So the question is this the final temp of the molybdenum, the water, or both? Molybdenum, yes. Water, no. Go slower, both. And the answer is both, because of something called thermal equilibrium. The definition of thermal equilibrium means they all reach the same temp, okay? So we want to figure out what is the specific heat of the molybdenum. So first of all, let's calculate the energy absorbed by the water. So we're going to call this Q of the water is equal to C of the water, M of the water, delta T of the water. The specific heat capacity of water is 1 calorie per gram degree Celsius. The mass of the water was 244 grams. The change in temp of the water is going to be the final temp, 15.3 degrees Celsius, minus the initial temp, 10. And when we do all the calculations here, just to kind of estimate, the difference here is 5. 5 times 244 is going to be roughly 1,200 or 1,250. So let's see what we get. 5.3 times 244, and I get 1293 calories. Now, according to the numbers that we have here, 15.3 minus 10 is 5.3, and it's only good to the 10th because of that guy. So here, this has 2 zig figs, this has 3, this has infinite, so this is only good to here. So our real answer would be 1,300 calories. Okay? Now, this is positive. So that means that this is endothermic, and the water absorbed heat. Now, what about the Q of the molybdenum? Well, where did that heat come from to heat up the water? It came from the molybdenum. Now, so the molybdenum is also going to be 1,300 calories. But is the molybdenum releasing heat to the water, or is it absorbing heat from the water? Well, I would say since it's so hot and it gets cold, it's releasing heat to the water. So what does the sign on the molybdenum have to be for the heat? It has to be negative. So this is negative because it releases heat to the water, which makes it exothermic. Okay, so let's keep that in mind. So now we have Q of the molybdenum is equal to C of the molybdenum, M of the molybdenum, changing T of the molybdenum. I think I'm just going to say Mo from now on. Okay, so that means that the specific heat capacity of Mo is Q of Mo over the mass of Mo, change in temp of the Mo. And I think something that has got us a little nervous is that the Q is negative 1,300 calories. So that makes me weirded out because I don't think specific heat capacity is negative. It should be a positive value. But let's see how it works out. So the mass of the molybdenum is 237 grams. The change in temp, well, the T final is 15.3 degrees Celsius. Initial temp is 100. Oh, and I see how it's going to work now. Do you see how 15 minus 100 is going to be negative? And a negative over a negative is a positive, so specific heat capacity will end up being positive. That's good. Okay, so let's see what we get. Divided by 237 and divided by parentheses 15.3 minus 100. And here I get 0.064 calories per gram degree Celsius. And if I wanted to convert that into joules, I would do this. And we would get 0.27 joules per gram degree Celsius. So here's the answer in joules per gram degree Celsius. Here's the answer in calories per gram degree Celsius. And let's see. Copper is 0.365. Gold is 0.129. So molybdenum should be in that rough area. So this is believable. Okay, so this is kind of what you're going to be doing as one of your labs, only you're not going to be doing this with molybdenum. Let me show you the drawing. So this is not what you're going to be doing with molybdenum because you don't have molybdenum. So can you think of anything that I could have you get the specific heat capacity of that we worked with in the past? Who wants to venture a guess? What could I make you get the specific heat capacity of?
Iron, I think.
What's that?
Iron. Iron or coin, copper or something.
Coins.
Yeah.
So I'm going to make you guys get the specific heat capacity of dimes, which you should know now are made out of copper for the most part. And I'm going to get you make you get the specific heat capacity of pennies, which you know are mostly zinc. And you're going to find out whether or not your experiment actually works out so that the specific heat capacity pretty well matches what you can find online for the specific heat capacity of copper and zinc. So you're going to have to find a way to heat up your pennies in a hot water bath and then transfer them to some water where you measure the temperature before and after. And of course, you're going to need a thermometer. And if you assume that the water bath is 100 degrees Celsius, here, this should be easy enough for you to do with a with a thermometer that you use to measure your temperature, because as long as the water is around your body temperature, it should be able to be measured. I'm not sure those digital thermometers, what their range is. Does anyone know? Well, we'll figure it out. Oh, and I should say, I'm going to have you guys come by and pick up some more lab kit stuff this week, Thursday or Friday. All right? Okay, well, thanks for listening. We've been at it for quite a while. Hopefully I'll see you Wednesday and we'll continue with this particular section. Toodles. Oh, turn your mics on and say goodbye.
Bye, guys. See you on Wednesday.
See you Wednesday.
Bye.